Now here, nearing the end of our topics, we get into a little bit more of the meat of algebra, and that would be relationships between things. Usually it's only two things as we start out with the algebra. So we would, at this stage, say a relation is a set of ordered pairs. So just pairs of things. I have one thing that's in a relationship with another thing. And all right, what else can we say about that? Well, two of the basic things that we can refer to are domain and range. The domain would be referred to as the values that come from the front half, the first coordinate in our pairs. And those pairs are ordered, so we can't just switch things around. That's not the way it works. First piece is first, second piece is second. So all of the values that come from the first part of our pair would be the domain. Now that's usually referred to by the letter X. Doesn't always have to be, but usually it is. The range would then be all of the values from the second half of our pair. The second half would be the second coordinate, usually referred to by y. Well, that kind of gives us a nice little tie-in here. If the first part of our point is referred to by the letter x, and the second half of our point is referred to by the letter y, x, y, those are in alphabetical order. Domain and range, D versus R, those are in alphabetical order. So there's a nice little connection here. X, Y, domain, range. We've got a nice little connection there that we can use to try to help us keep track of those things. And so literally, if they were going to give us some sort of relationship, they could list out the pairs, which would mean that the first number in each pair, which has been underlined in blue, would correspond to my domain. So I would want to go ahead and collect all of those numbers together into a set. The second numbers in each of those pairs would correspond to the range, so I would collect all those numbers together for my range. That's one way of presenting things. They could give me a relationship instead that would be based on a table. For instance, a table like this, certain ages of people that are in a class, how many of those people we have for each age. Age, in this case, being listed as the X, so that means the domain would come from those ages, and the Y is that frequency, how many people for each age, those literally coming together in our range. Excuse me. And they could also give us what we refer to as a graph, a picture version of a relationship. So in this particular case, the picture that they've given us in orange represents all of those different pairs. And if we wanted to figure out the domain and the range, we would have to look carefully at the way that this has been drawn. The domain is supposed to come from the first half of each of these pairs, which we say usually is labeled with the letter X. And the letter X is being labeled here as left to right. The second half of each pair, usually labeled with the letter Y. In the drawing here, the Y is being labeled here as the up and down. So for the domain, what I would want to do is smaller to larger, see where the orange drawing appears. How far to the left does that orange drawing appear? Well, there is no orange to the left of that bullseye for my little grid here. That's what we call the origin, by the way. It's right smack there in the middle. So if that's where the orange starts, and we literally do get to land there, I can put my finger right there on the orange and be on that spot, then if I'm allowed to include it, I've got a bracket. Now coloring in, the orange that I see, I'm coloring in along the bottom, I see orange off to the right, off to the right, off to the right, then I see those arrowheads telling me that that orange is going to continue to appear further along off to the right, though I do not any longer need to show more of the drawing to get that idea across. That representation points me to my domain. What is the number there right where that orange stuff starts? Well, that would be not having moved from the bullseye. So not having moved, 0. Going all the way off to the right forever and ever, infinity. So using those same sorts of ideas that we had when we were working inequalities, however long ago that was, the range is taking a separate look at things. So the way that this up and down works, smaller is down, larger is up. So if we want to write our range from smaller to larger, then we would want to look at our orange drawing here again and say, starting at the bottom, how low or how far down does that orange seem to go? Well, when I look all the way down at the bottom of what's been drawn, I have an arrowhead, and that arrowhead does still point into the downward sort of direction. So it does keep going down, 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 which means that my range, well, is going to end up incorporating all of those negative numbers that are down, down, down. As I look at my orange drawing again and start moving upward, I end up seeing that I've got another arrow that also points upward, and that would mean my range is going to continue to go up, up, up. So without any sort of weird occurrences in between those two observations, our range would go parenthesis negative infinity, because it goes forever down, comma positive infinity, because it goes forever up, and there's nothing weird in between. But not all of our graphs have to look quite so smooth and connected together. We could have things that seem to be, well, just kind of pieced together with very little rhyme or reason. What we have in this example is a drawing, a graph, that appears in pink. The solid dots are places that we can literally land on. The pink parts that are drawn in a solid weight, those are places where we can land. Open circles, well, kind of think of it like a pothole. You don't want to just go hopping into potholes with feet or with cars. So those are spots where we do not get to land. We'll just right through. Bottomless pit, kind of a goofy way of looking at it. Bottomless pit, you know, no place to land, no place to stand. So I want to make sure that I understand that those are the kinds of landmarks that I am seeing here in this picture. And if we want to identify the domain and the range, I need to be aware of those things. The domain, again, is going to be based on the x, which runs left and right. So I want to go from smaller to larger. Down along the bottom, I'm going to look as far to the left as I possibly can. And what I notice when I do that is that the pink drawing does not go any farther to the left than this pink dot right here. According to my labels, since I don't have any numbers, I'm going to just assume that these go by 1. So moving to the left, -1, -2, -3, -4. There isn't anything further to the left than the -4. So that's where my domain is going to start. So I can come over here and actually start filling in part of that domain by using that bracket and the number -4. And then we'll put our comma in there and see kind of what happens as we continue to move along. As we start moving from left to right, we got the pink, so that we'll go ahead and color this in with our little blue highlighter. We got the pink, we got the pink, we got the pink, we got the pink. We come all the way up to this other dot here, and we do get to actually land on that dot. So our blue highlighter can come all the way up to where that dot appears. And now we've got to worry about now, if we can continue moving to the right past that dot. Now I don't particularly care whether I'm skipping around from one piece to another. I just simply want to know, can I color in numbers from the left to the right without having any sorts of breaks or jumps or holes to worry about? So far we've said we can go ahead and cover all of the numbers up to the -1 where this dot is. We need to know, can we immediately continue coloring other numbers that are between -1 and 0? So do we have somewhere pink drawing that is in between the -1 and the 0? We sure do. It's on a separate piece, but we do actually get to cover those numbers. So while we do have to jump to another piece to cover them, we do cover them and continue to move off to the right, and we go far enough along, we actually see that we get that arrowhead pointing still farther off to the right, so that there appear to be no breaks in the numbers that we cover as we move from left to right. So our domain would finish up with the positive infinity symbol and always a parenthesis beside that. Having jumped between this left-hand piece and this right-hand piece did not affect how I covered the numbers from left to right. I covered all of the numbers starting at the -4 all the way up to the -1. I can immediately move past the -1 and still see pink drawing somewhere. Yes, it's a separate piece, but I can still see pink drawing covering the -1 to 0 to 1 to 2 to 3, and there's where my arrowhead is, saying, hey, that sucker's just going to keep on going, keep on covering numbers as you keep moving off to the right. Now the range is a different story, where we would want to maybe think about tilting our head, and so that it works out, so that we can kind of see things the right way. Or if you're writing on paper, it's a whole lot easier. You just turn your paper so that what you're doing is looking at bottom to top, but you can still kind of say, well, because I turned my paper or I turned my head, I'm still looking at things kind of from left to right. So from lower, smaller to bigger, how do things work out if I am viewing things like that? The farthest down that we can go is that pink dot that we have. And if we count out the marks, that pink dot would be at the -3 marking. We can use our green highlighter and start coloring in as we move up, 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 up. And we get to this other pink dot, and we do in fact land on that spot, but as soon as we move past that spot, I don't see any pink in this section here. I have a gap where there is no pink stuff between a -1 marking, and I've got to come all the way up here to where the number 2 marking is. So I've got a big old gap. The last spot that I'm able to land on here for a moment is where my y is a -1. And I do get to land there. then there's a big old gap before I get to pick back up. And when I pick back up, that's where I have that circle, this bottomless pit kind of thing. I can't land there in that circle. There's nothing to physically land on. It's empty. Whew, fall right through. Bottomless pit. So I can't land on that. So I'm using a parenthesis here to represent that that's not included. That particular number where y is a 2, that is not included. But as soon as I move past that circle and start looking farther up, I do get to continue on and eventually see that arrowhead again, which is pointing in the upward direction. So the rest of those numbers do get covered by my little green highlighter. Looking at things that way means that we would have the infinity and the parenthesis, but we are missing one last thing, because officially I have two separate pieces, and the range and the domain are supposed to be one set. So this is one of those occasions where we pull out the union symbol to join those two together in order to, instead of having two separate sets of numbers, we now officially can see this as one big set of numbers for the range that take care of all of the stuff in pink from bottom to top. Well, relationships are one thing, but in math, we'd like to have a little bit more to be able to hang our hat on. So, if we consider very special relationships, very special pairs, then we can have something else happening here that is worthwhile to note. A function is a relationship where the x is paired up with no more than one y. So the cute way of putting this is x doesn't have to be in a relationship. So x could not be paired with a number. X is single. That's allowed for functions. X could have the boyfriend, girlfriend, fiance, wife, husband, but only the one other thing that the X is in a relationship with. Having that would be a function. If the X has a boyfriend and a girlfriend, not a function. If the X is in a polyamorous relationship with 4 other people, not a function. If the X has a wife and a mistress, not a function. The X is single, or the X has a significant other, one significant other, period. So, kind of the conservative math. X is allowed to be single, X is allowed to be in a relationship with one other thing, we would have a function. Any other situation, not a function. So if we look at these lists, the 1 is in a relationship with 2, the -1 is in a relationship with 3, the 0 is in a relationship with a 4, a -2 is in a relationship with a -2, a -3 is in a relationship with a -5. None of those first numbers showed up as being in a relationship with more than one other number. The number 1 is in a relationship with the number 2, not with any other number. A -1 is in a committed relationship with the 3, but not with any other number. So, in this particular case, we do have a function How about part B? The 0 is in a relationship with 1. A 1 is in a relationship with 2. 1 is in a relationship with negative 2. Whoa, wait a minute. The 1 has himself 2 little somethings on the side. The 1 is hooking up with a 2 and a negative 2. That ain't allowed. That ain't allowed for a function. So this is a no, not a function, because 1 is attached. Let's not be crass and say hooking up. 1 is attached to both 2 and negative 2. That's a no-no. Function has a very strict sort of allowance. I refer to that single idea. Let's kind of look at that back with the first example here. There are a lot of other numbers that we didn't have showing up at the front half of our pairs. For instance, we didn't have a 10 that was paired up with anything. So the 10 would be considered single. The 10 is not attached to another number. It's single. That's allowed. The fact that the other numbers in the front of each pair only are attached to one other number is the other part that we've got to worry about here. So all the other numbers, like a negative 25. Negative 25 is not attached to another number, but the 0, is it attached to only one significant other? The 1, does it have only one significant other? Nope. Not a function. Transforming that idea into a visual representation gives us what we call the vertical line test. Since the x goes left to right, each one of my x's could be single, there's no drawing that shows up, or it could have one significant other, which means that it would hit my drawing, my graph, in one spot. Anything else is a no-no. So over here, my x's are single. As soon as I hit this very tip-top spot right here on my orange drawing, that x is in a relationship with only one other number. But over here, this x is in a relationship with 2 different y's. It's in a relationship with this one up here and that one down there, and that is a no-no for functions. If I have even one vertical line that hits my graph more than once, then it fails the test. It's not a function. So that means that we can look at some other pictures and kind of test things out about whether the drawings that we have would represent functions. So the arrowheads are still an important sort of thing to recognize. Way off to the left side, the arrowhead says I eventually would hit this particular line. This green drawing here is a line. So each time I'm looking from left to right at those x's, one hit, one hit, one hit, one hit. Everything seems to be fine with that particular drawing. So we would have said that this one is a function. For the next one, we've got this oval shape, and we move far enough along that we would see that in that oval shape, if even one vertical line hits more than once, we do not have a function. Moving on to the third, a little bit of a kind of roller coaster appearance there. Hits once, hits once, hits once, 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 once. And despite the fact that that arrowhead here, mellow, kind of keeps going down, that one's a little steeper. The thing is that if I looked close enough up, none of those vertical lines would be hitting more than once. So everything is actually just fine in that particular picture. And considering this last drawing here off to the right, hitting once, 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 oof, shucks. Right there, that one vertical line right there, that's the only vertical line that hits this drawing more than once, but all it takes is one vertical line. So the fact that we've got the one vertical line that's passing right on through both of those dots means that in this particular case, this is not a function. Well, it'd be nice if they just flat out told us when we had functions, if they would, limit how much they nagged us about finding functions for ourselves. And it turns out that they do. If it's so darn special that it has its own name, function, then maybe there's a nice special way of using some notation to represent that we have a function. And yep, there is. We need two pieces of information to identify a function. We need its name, and we need to be able to say what the variable is supposed to be. So f would refer to the name of that function. X would refer to the variable that is part of that function. Usually we use x, but we don't always have to. And usually they use the letter f for the name, f for function, but that gets kind of boring, and frankly, there's obviously with people and anything else, no need to stick with one name. Not every guy is named Bob, not every gal is named June. So can we name functions other than f? Heck yeah. And so here are some other examples where we can have those different kinds of names and those different kinds of variables that show up. So practically speaking, we might think about things that are actually available in real life where what changes, like a variable. X could change? Sure, that's super generic though. What in real life changes? Well, shoot, right now, gas prices changing because there's a hurricane a-coming. So if I have price and there's some sort of function of price that could describe how those gas prices are behaving and other things that might be going on. What else? Well, shoot, every time I move, time ticks by and where I am changes. How fast I'm going changes. And so I could have other functions that are based on time that give me things like position, speed. I'd want to represent those kinds of things as clearly as possible. I wouldn't want to just use f of x every single time. Snooze fest. Let's change it up. When we can be a little bit more on target, let's use an appropriate name, let's use an appropriate variable. And we have that freedom. The notation itself, the structure of it, is what makes us identify that's a function. I don't need to figure that out. They're flat out telling me right from the start. Score. Now, we would want to be able to evaluate functions, and this brings up the other option that we have for having a relationship given to us. Not just a list of pairs, not just a table, not just a drawing, aka graph, but they could also give us an equation that has two different variables in it. And if they use the function notation, then that means that they're already telling me right off the bat that I have a function. G of x is equal to x divided by x squared plus 1. There we go. We have a function because they're using the notation. They're telling us exactly how we can calculate the second half of each pair based on different choices that we might make or different numbers that we might be forced to plug in. Evaluating. Instead of a generic letter x for my variable, if I have a number or a different looking expression, I would replace my variable with that number or that expression. In our example here, instead of g of x, I have g of 0. So I'm going to replace the x with 0. Everywhere in my equation, I'm going to do that. So 0 on top, 0 on the bottom, and I'm going to crank out that calculation and figure out what that second half of the pair is. If the first half of the pair is a 0, the second half is a 0. There's my pair. G of negative 2. Instead of the x inside those parentheses, I have the number negative 2. So in my equation, instead of the x, I'm going to put in the negative 2. If we crank that out, up on the top, we would have our negative 2. Down on the bottom, we would have negative squared is a positive, 2 squared is 4, 4 plus 1 is 5. So the second half of our pair would be a negative 2 over 5. In part C, g of x minus 1. Well, now instead of x, they're actually telling us we're going to have a different expression, not a number, but a different expression. So we're going to be replacing the x with an x minus 1. My equation says up on top I have an x. Well, I'm going to replace it with an x minus 1. Down on the bottom, I have an x followed by a power of 2. I'm going to replace the x with parentheses x minus 1 so that I can put in the power of 2 and have that working correctly. But after the power of 2, I also have to have a plus 1 in that denominator. I could continue to tinker with that, but there's really no point in doing so. My point with that particular example is again to say we can replace the x with anything that we might want or anything that we might be told, whether that's a number or another expression. We can replace the x with anything at all that we either choose or are instructed to do. And so in this part D, g of 1/3 means that we would replace the x with 1/3. And again, according to my equation at the top of the screen, that means that we would have a 1/3 on the top. Down on the bottom, we would have to have a 1/3 being squared, followed by a plus 1 down there in the denominator. This is something that, yes, we can simplify, so we would have to go through our steps or possibly use our calculator to work that out. 1/3 squared means 1 squared on top and 3 squared on the bottom. The denominator would also have to follow up with that plus 1. That means that down there in the denominator, we would need to get a common denominator and add those together. Common denominator for these would be a 9. So a 1/9 plus 9/9. That would give us a 10/9 for the fraction down there. But this is, and has been since the very beginning, very aggravating because we have a fraction on top of another fraction bar So let's go ahead and try to rewrite that in a much friendlier fashion, where we would have the 1/3 divided by 10/9. According to our rules for dividing with fractions, keep, change, flip, 1/3 times 9/10, multiply straight across and simplify, and that would give us our final value of 3/10, meaning that our ordered pair would be a 1/3, comma, 3/10. Again, function is giving us the second half of our pair. Or we could also say our function values are y values. We either pick or are told what the x values are. So when we crank out these values from our functions, those are just y values. We don't want to lose sight of that very simple sort of fact. Now we do want to revisit that idea of domain that we talked about at the beginning of the video, as well as come back to some of the other things that we have seen in the past. So some of the functions that we have are things like a 2x minus 3, other things that have other powers in them. We could have things with rational expressions. We could have things with roots. What kinds of issues do we have? Well, if all we're going to do is multiply, divide, add, subtract by other numbers, if we're going to raise things to powers that are not weird, like negative powers or fraction powers, then it turns out that we actually don't have anything particularly funky going on with the numbers that we are allowed to plug in for x. We don't have anything funky going on with the domain. We're allowed to plug in anything and everything that comes to our minds. If we've got a rational expression that shows up as part of our function, we would have to worry about, and I think we've said this before, just not quite in the same way, we're not allowed to divide by 0. Anything that creates a 0 in our denominator would need to be thrown in the garbage, and in this particular case that means x would not be allowed to equal a -7. But everything else is fine. So we throw the -7 in the garbage, and everything to the left of it is good. Everything to the right of it is good. Use the union symbol there to join those two separate pieces into one big old set. And we said back when we were talking about those roots, those radicals, even roots, the stuff underneath and the even root has to be greater than or equal to 0. Well, that would definitely be the case with a square root. So the x minus 4 underneath that square root can't be negative. It's got to be greater than or equal to 0, which means that the x specifically would have to be greater than or equal to 4. So I could do the domain that way. We've incorporated that already with some of those other discussions without quite spelling it out in the way that we now have. We are talking about the domain. What numbers are we allowed to plug into a function? Is there anything that we would have to worry about based on what we've been given? Any sorts of restrictions, like we're not allowed to divide by 0. The numbers underneath of even roots can't be negative. If we have any sort of restrictions like that, then those could have an impact on the domain. Those could have an impact on the kinds of numbers we are allowed to plug in. So the domain and the range are a couple of those basic things that we've got, and through the other discussions that we'll have, we'll find some of the other things that we can try to use to help us with understanding and analyzing functions.